Hi all, welcome to the Big Data and Hadoop an introductory session. Um, to introduce myself, I am Bhaskar Kali and I have been in this Big Data and Hadoop industry for years, and I will be the presenter for this, which is also a demonstration session and also sort of introductory session for people who do not have the Big Data and Hadoop background knowledge. Now this is being given, sorry for that, on behalf of ITST, who is a specialized training services providers for next generation technologies and consulting. They have dedicated trainers for each and every extensive areas that is addressed to the needs of the participants. They have been a provider on big data and Hadoop technology, which is most prevalently sought out today, and obviously the cloud and Azure platforms, and other than that, they also offer PMP, ITIL, and marketing certifications too. Now, in this introductory session, we will look at about big data and Hadoop in specific. What is Hadoop all about, and what is it made of? And also, we will have a look at Hadoop's ecosystem tools like Pig or Hive. And then I would conclude my session with some of the Hadoop career opportunities and its promising salary levels and job responsibilities to the people who are seeking options in this area. I will also touch a little bit about the prerequisites that you need to learn this and to familiarize with yourselves, but not to panic. There's not much of a prerequisite there. Now, what is big data? I mean, in order to go and talk about big data, you guys need to understand what is data all about, right? The data is a piece of an information, right? It's raw. It's not processed. We call it information once it is processed. It's a raw piece of data, and when processed, and we use the information after processing it to make a decision making on a certain context. For example, you are going to a showroom and then you are asking for a television. Now, television is the data. It is raw, right? And you ask for a television, and then you build it upon it, so to say that you need a Samsung television. Now, you add up the data to process information on it, and then you go choose the thing. So it is used to identify what sort of a television that you are looking for. So that's where it's all about. A data is vital to make a key decision that is going to impact a business opportunity or predict a certain behavior, or to provide further information that will lead to the change of the way we operated in the internet world. Now, this slide is pretty much self-explanatory, but to give you a gist of it, as we are talking about, as we are listening to this class, we just see millions and zillions of data floating around the internet. Now, when internet was formed in the year 1970s by DOD, I mean, not much has been thought about that this would be a monstrous thing that is gobbling the whole world today. And if you see, we have multiples of websites that's been thronging right from various domains such as professional, personal, and shopping, entertainment, and in various categories. I mean, we do have things in terms of virtual reality too. The sites such as Flickr, Twitter, Facebook, as you see in the right extreme part of the slides, relate to the personal sites, which pumps in data of in terms of terabytes every day, and then we go to the shopping sites, and then we go to the other sites. So if you see, each and every site is being, the data is coming into it. Now, when we say data is coming into it, it is getting into a server, right? And now, can we put all this information? If you see the data, and if you see the data that is coming from Twitter, they say it's like 100,000 new tweets in a minute. Now you can understand how much of a data it could be. So as we talk about, we see that around 639,800 GB of data is being transferred in a minute. Now, can you put these things in one monstrous servers? Now, the answer is, you can think how much of a server capacity that we would need then. So answer is obviously no. We need to find a new ways of putting this, new ways of tackling the problem, because one thing is now you've got to store the data here, this much of a data, and another thing is, okay, we stored the data, but how are we going to fetch the data and process them? Now that's what we call as a big bang of internet, because too much of information exploding in a certain fraction of time, and we got to have a mechanism to deal with this big bang. And the future growth is staggering to an extent that it is going to grow into more than the population that we are having currently in the world. Now that's what we are talking about. We are talking about big data as such a massive volume of data, which is the big bang of information that's flowing across every minute. Now when we deal with this massive of information, for example, I may ask you, if I ask you to lift like 10 kilogram of weight, you can lift it. But 20 kilogram, yes, you can do it. But 60 kilograms, you can do it. Can you lift like 600 kilograms? No. You got to break it down into little by little, and you got to have an approach to lift that, right? That's what we're talking about. Like big data, when it's massive volume of data, can you handle everything at once? Absolutely not. You got to break them down into chunks of data, chunks of sizes, and then you got to process them on the chunks of sizes. But first of all, before we process, we got to know how do we store them. First of all, how do we store this massive amount of data into a hard disk, which is not one monolithic hard disk, because we can't find one monolithic hard disk. And the beauty of big data is that it is into three different varieties here: semi-structured, structured, and unstructured, right? For example, the Facebook post, it could have text, it could have a video, it could have a voice or emoticons. Now, we can't define a certain structure to the big data. So this is what we call as three big V's of big data: the volume that deals with the amount that's being transacted, and then the variety that deals with the types of information that's been transacted, and then the velocity, as we talked about, it's a big bang of information that's flowing, and how much of it is flowing every second counts in here. Now, every data, if we got to attribute to big data, they got to satisfy these three V's. They got to have these three V's. Then you can construct them or tell them that that belongs to big data, and probably you can have a big data approach to solve the data to make a decision. What are the challenges in it? Absolutely, we have a problem in finding the right data. I can give you an example. If you go to a shopping site and you want to, such as Amazon.com, and you want to buy a television, you are reading the user reviews, right? So when you read these user reviews, you see some of the good reviews, some of the bad reviews. Now, how do you trust actually? Is it right data or wrong data? Because there are, it's a user review. I mean, they can put wrong information to demean the product or demean the company because they have some sort of a personal vendetta or probably a problem associated with the person who dealt with him. So how do we really deal with the right data to actually assimilate the information that we want? That's one of the big problems that we got in big data world. And not to mention that there are solutions evolving, which we will talk in detail during the classroom sessions, but there are solutions evolving, and with respect to genuineness of data and correctness of data. Yeah, the second big challenge seems to be the talent, because big data industry is an evolving industry and it's quite a new industry. In that case, the people needs to be having such certain defined skill sets, and that seems to be a big challenge today. And absolutely, big data works on the internet world, so connectivity seems to be the biggest necessity here. If there is no connection to internet, there is a problem in dealing with the big data. So we also deal with multiple problems of security because we are dealing with internet. So big data does not come with just benefits, but it also its own challenges. But as somebody rightly said, every challenge is an opportunity, and that gives way to newer avenues to explore. That's where our guy, Apache Hadoop, comes as a killer to handle this person. Now, what are the bigger problems of big data? The data that needs to be stored, the data that needs to be fetched. Now, that's what Hadoop is all about. Hadoop is a solution to approach the problem that the big data is posing to facilitate writing the data and reading the data and processing the data in an effective and easier manner when we are dealing with such a big amount of data. So it's basically, in plain words, it's just a software framework that is written to deal with this big data. Okay. It's not just newly born today, but it's been in the industry for the past decade, and it's been slowly making its own way. When it was formed by Doug and Mike Caravella, two Harvard graduates, colleagues working on the working on the Nudge project, which got adopted by Yahoo later, and then got spawned as a Hadoop and given to the open source industry as Apache Hadoop, and that's how it slowly started getting significance. And since then on, big data has never looked back. Since then on, Hadoop has been a winning software to approach the problem that the big data was posing. So this slide itself is a timeline slide, and it talks about how the Hadoop actually originated from the Google's papers, from its file system and MapReduce algorithm. Now, MapReduce is a key word here. You know, you got to map it. You got to map multiple elements of the data, and you got to reduce them once you map it, and that's what it's all about. Now, if I ask you, there are like 10 dumbbells, and every dumbbell weighing 1 kilograms, and I'm giving you a 10 kilogram weight. You got to break them down into 10 dumbbells, and then I am asking you to lift them. You got to lift them like 2 each, or all 10 together. Then that's what it's all about. The big data is broken into chunks and stored into the server, and that part is dealt by the Hadoop distributed file system, HDFS, as you see right up in this slide. And then once it is stored, then the way it is fetched and worked on is the MapReduce part here that you see. So this relates to the storage part here, and this relates to the computing part here, and both combined forms Hadoop core. You know, and Hadoop core is a setting stage for big data processing on top of it, using ecosystem tools such as we see here: Pig, Hive, HBase, Flume, Scoop, and it's been like going on and on and on. And of late we have been going through the Spark and Storm, which facilitates real-time processing of the data too. Now, when we talk about HDFS, in plain words, it's a file system. As a file system resides in a hard disk, and HDFS resides in any machine's hard disk. Now, the beauty is that you don't need a dedicated server. You can just put them on a commodity mission, such as laptops. Now, this set of missions running them is called the cluster, okay? And every individual mission is called the node. Now, you want more data, obviously more the nodes is needed. And when more than nodes are there, obviously more the processing is required, and that's where the MapReduce comes as a killer here. Its characteristics: HDFS is very reliable, which means that even if one system goes down, it can recover the data from the other system. It is scalable because we're talking about a bigger size of a data here, right? So we can't fix a certain architecture. The architecture needs to be scalable. As the data increases in size, you got to have facility to scale the storage system so that they can be stored. And as we already said, that it can run on commodity hardware, so which means it's cost effective. We don't need to hire like mainframe machines or high-end blade servers to run these things, such as the case used to be in the olden era. And Hadoop comes and defeats the whole purpose of it. And Hadoop has a flexibility to deal with both structured and unstructured. Just now we talked about the Facebook example of having a text and a video and things, and Hadoop can differentiate between them and process them. And Hadoop works on the file system on write once, read multiple technology like worms, which means that you write once and then, which means that, you know, for example, if you tweet once and you don't change the tweet every time, you may add a new tweet but not changing the same tweet, right? That's what it's all about. So for such kind of a data, Hadoop is suited for it. Yeah, and the change why Hadoop is more prevalent is because in olden days when we wanted to do compute the data, we used to take the data to the processor and then the processor used to work on the data, right? But now we're keeping the data stagnant, we're keeping the data on the hard disk, but we're moving the computation to the data, to where the data is all about. And now why do we need to do that? If I need to work with 2 kilobytes of data, it's much easier, you know, I can move around an interface. But if I need to move like 2 terabyte of data, and the time going to take to move the 2 terabyte of data to my processor itself is longer. I have no patience to wait because there's an ever-changing world in the internet, and there is no patience there. So we need to arrive at a faster way. So which means that we move the computing, which means we just move the way it is processed to the data and to where the data resides. And obviously it's fault tolerant since the hardware failures can be managed, and it's a software platform, which means it provides APIs for the users to develop applications on top of it, and it uses simple file system model, which means you can open a file, write things, and then close the file. You don't need to bother about structuring the data at all. It's a flat file system. You don't need to bother about the hierarchies and things like that. Hadoop comes in 2 flavors, 1.2 and 2.0. Now 2.0 is the most advanced version, and it provides more facilities to operate with it, including the real-time part of it, which is better than 1.0, but more or less the framework is more or less the same. And the difference you see here is from MapReduce and the Eon part, the way the resources are managed, the nodes. When I say the resources, they are the nodes. And the way the data is processed, they are a bit different across 1.0 and 2.0, but the basic core remains the MapReduce here. As we see, we can support many kinds of applications such as batch processing, interactive, online streaming, graphing, in-memory, and MPI for the mainframe thing on top of Hadoop. So Hadoop is an answer to migrate the old traditional data systems to the newer Hadoop-based big data systems. Pig is one of the Hadoop ecosystem tool, and now Pig is why do we need an ecosystem? You know, ecosystem makes our life easier to use the framework, right? So Pig is one of the tool built on top of Hadoop, as you see here. Where is that? Yeah, it's built on top of Hadoop to ensure that the data inside the HDFS is processed in an easier way, and it is aimed at people who are scripting language skill sets. Because it's a data flow language, the input of the data is the output of the data is the input of the next data. So that's how it goes, and it's good for structured data, which means that if there's a structure, Pig can work easily. Obviously, Pig is an interpreter language, so as we said, it's a scripting language, so it's slow. So we will learn about this why it is slow in the detailed things. But for an introductory session, you just got to keep in mind it's slow. Now Pig has 3 components. One is embedded, which is on the Hadoop part. One is a grunt, which is a shell, and one is a script. Now this is where we programmers will write the job, and this is where we run the job, and this is where the job translates into MapReduce. Now a Pig program transforms into multiple MapReduce jobs to get the results of the data that is being processed, and that transformation runs on the grunt shell. These are some of the operations that we can do it using Pig. We can load a file and store a file and see the file using these 3 commands. We can do the filter operations, you know, and join operations and sorting operations and combining operations. Now, this is a basic comprehensive set of commands that we got to use Pig to load the data, to do anything with the data that we got. In this example, we could actually see, if you see, this is a sample code of a union example, and here we just say load a file here called data1 and load a file here called data2, and we are loading what in data1? 2 integers, a1 and a2, and here in data 2, B1 and B2, two integers, and they are stored in the variable A and B, and we are performing a union of these two, and then we are just seeing what is the result. Now that's what we see the data file here, and we see the union of it, we get the union of it. Now you can see the pick script. It's so easy to load and do the union operation with the pick command list that we have seen here. Similarly, there are many. Similarly, we can have programs for different types of characters. For example, float and character arrays. We can group them, we can co-group them, we can filter them. So we can do multiple operations using pick to process on the data. We can do join operations. Now, while pick is more used for scripting language, Hive is a key there, because Hive is some sort of a database-oriented language for people coming from SQL background, where people can write SQL-based commands to work on the Hadoop data, right? SQL-based commands are used majorly on the databases, but Hadoop is not a database. Hadoop is a file system. So how do we ensure that the traditional commands can still operate when the data is moved to file system-based storage? Now that's where we need to think. And that's where we have an ecosystem tool called Hive, which is more of a SQL language designed to work on Hadoop. It defines SQL query-like language, and it suits for the data warehouse infrastructure. It also provides the ETL processing things, and everything runs as a MapReduce jobs. In turn, you can also write custom MapReduce jobs in Hive. Just like in Pig, we saw three components. What are three components? Grunt, Embedded, and Script. In Hive, we have similar components such as shell, like Grunt, Metastore, Engine, Compiler, and Driver. Driver is used to connect to the database. Compiler absolutely is used to compile the Hive script, SQL language. Metastore is an internal database that it stores. Hive also provides all the facilities like SQL. You can filter a row, you can store the results of a query, you can do equi-joins, you can partition the table and join the tables. You can also query from a Hadoop file system directory. Where is it used? Hive is one of the most prevalently used ecosystem tools. You can mine the data to do some analysis on the data. You can do log processing, you can do BI processing, you can do predictive modeling techniques, and you can do document indexing with Hive applications. This is the Metastore that we are talking about. Why we need to do Metastore? Because for SQL works on a structured way of operating things, and we need to have a structured mechanism. That's the reason we need to have an internal database built called Metastore to store the structures. And it can be internal or it can be remote or local, where we need to have a driver to communicate. Absolutely, Hive, because it's running on top of Hadoop, it has all the problems of not suiting for an online processing and not suiting for real-time processing, and it is slow with respect to the queries, since it is not a real-time thing, and it is not suitable for interactive data processing. This is sample Hive architecture, and if you see, Hive actually stands on top of Hadoop, and Hive has the driver, ODBC drivers here, and compilers here, and a command line interface, and hardware interface, and a thrift server to handle different kinds of data. On top of it stands a business analysis tools such as Karmasphere, Cubole, everything. And if you see, the data is actually stored on the DFS here. Yes. Now, given the fact that Hadoop is really prevalently being used to attack the problems of the big data world, there's tremendous career opportunities that Hadoop provides, and then the statistics indicate in 2015 itself, 4.4 million IT jobs will be created, and just around half of it will be in the States itself. This is done by Gartner Research, and the Gartner Research predicts that Hadoop will be one of the most demanding technology in the big data industry, and it's been increasing exponentially in terms of investments. You can see it's like gone like sixfold increase from what it is there in 2013, and this is a strong prediction that Hadoop industry is going to grow in terms of big data. There are multiple levels of job levels. Hadoop offers. One is the administrator, which is much like the network administrators and Unix administrators, who tend to set up cluster, manage the cluster, do partitioning and things like that, who set up the tools, ecosystems. Developers who write the MapReduce programs on Java or even using one of the ecosystem tools. Business analysts who tend to use the information given from the MapReduce and try to make a meaning of it. Data scientists who try to verify if the data is genuine or not, and architects who try to design the systems. And almost all the companies who are leading this space are hiring, if you see all of Fortune 500 companies, and they are prevalently the Hadoop-based technologies. I mean, the slide is self-explanatory that more than 17,000 employees are employed by these companies with Hadoop skill sets. Salary levels, actually, if you see the current trend, the most wanted technologies are SAP and Hadoop and other web-based technologies, and Hadoop is actually leading the pack with roughly around 100,000 K USD per annum for somebody having Hadoop skills, and it is actually exceeding everything, even SAP and Unix. Okay, so it pays well a lot to learn Hadoop and master it. Now, this is the summary that we have come across, and in the detailed training, we get into the details of architectures such as what is actually contributing to HDFS and MapReduce and Yarn, and we also get into the details of Hive and other tools such as HBase and Spark, etc. And we probably have some projects to deal with it. So that's all about the introductory session today that we had. If there is any questions, we can go ahead. Otherwise, we can conclude this session.